So in cryptography, we learn various methods of encryption and decryption. So we've seen two significant ones so far. One is the Diffie-Hellman key exchange, which is based on the mathematics of the discrete logarithm problem. We look at the RSA crypto system, which is based on factoring integers and solving congruences for powers. And today I'm going to describe a third crypto system for sending messages, a public key crypto system, which is based on what are called subset sum problems. And these are also called the so-called knapsack, this means backpack, crypto system, which is based on a completely different kind of mathematics. So it's important to see how different kinds of mathematics are used in cryptography. And that's what we're about to do. So the subset sum problem is the following. Suppose you're given a list of positive integers, M1, M2, M3. So this is a sequence. They're not necessarily in order, not necessarily increasing, not necessarily, but they are positive integers. So you're given a list of positive integers, and you're given an integer s. And what you're told is that, so this is what you're told. S is the sum of a subset of the integers, and I'll call this sequence capital M, in M. And you have to find them. So here's a simple example that you find in the beginning in this section of the book, section 7.2, chapter 7, page 377. Suppose M is the set of integers 2, 3, 4, 9, 14, and 23, and S is the number 21. So we're told 21 is a sum of a subset of these integers. Find the subset. And I think if you check, 21 is 14 plus 7, 14 plus 4 plus 3. So the problem is find the subset of M that adds up to 21, and it consists of the numbers 3, 4, and 14. Suppose we have S equals 29. Find the subset of this set that adds up to 29. Let's see, I could take 23, and then I need to get 6, so 23 plus 4 plus 2. Actually, it turns out I can do it another way. I don't have to take 23. I could take 14 and 9 and 4 and 2. So the solution to this problem is not necessarily unique. There could be more than one subset of M that adds up to S. But the problem is, or you can think of this as a mathematical problem, as a puzzle. I give you a set of integers, and I tell you there's some number S, which is the sum of some of the elements in the set M, and you can't use any element more than once, find the numbers that add up to S. Now, there's an alternative way to write this. So let's, for example, let's look at 14, 4, and 3. So 21 is, let me just write it in increasing order, going from left to right. 3 plus 4 plus 14. If I look at all the numbers in this set, that's really 0 times 2, 1 times 3, 1 times 4, 0 times 9, 1 times 14, and 0 times 23. So it's like I'm adding up all of the numbers in this set, but each of them is multiplied by either 0 or 1, and it's 1, then you're really adding it up. Otherwise, it's 0. But if I look at the sequence of zeros and ones, that is a sequence of zeros and ones. If I let X be this sequence, 0, 1, 1, 0, 1, 0, I can say this bit sequence, the bits or zeros and ones, this binary sequence corresponds exactly to this subset sum to the number S equal 21. So another way of describing a subset sum of a finite sequence M is you take a sequence of zeros and ones, and that tells you, when you look at the corresponding sum of the elements of M multiplied by the appropriate 0 or 1. So let's look at another example of that, just to make sure it's clear what I mean. Suppose I have, again, that sequence M, which is 2, 3, 4, 9, 14, 23. And let's say I have a message I want to send to someone. And I can write every message as a number, but I can write every number in binary. So a sequence of zeros and ones is the equivalent of a number. So suppose I have a message X to transmit. And suppose X is some sequence. Let me just write it as, I don't know, epsilon 1, epsilon 2, epsilon 3, epsilon 4. Well, actually, I can just use X's. Easier. So X is a bit sequence of length 6. X1, X2, X3, X4, X5, X6. So I take this sequence, and these Xi's are all 0 or 1. And corresponding to this sequence, I take the sum S, which is X1 times the first number, X2 times the second number, X3 times the third number, X4 times the fourth number, X5 times the fifth number, and X6 times that's a 14, times 23. So this is some number, it's a subset sum. And I can transmit the number S, and the person who receives it, who knows the sequence M, just has to figure out what sum of elements of M gives me the number S, and that determines this bit sequence. So in a certain sense, you can transmit a bit sequence by converting it into a subset sum of some set M and sending that number. And then to decipher that, you just have to break this number up into a sum of elements from the set M. Of course, occasionally, as we saw a moment ago, some numbers have more than one representation. So there's as a subset sum. So you might have to deal with that. But if you take big, long strings, that's not going to happen. But this is the idea that you have. So there are three ideas here. You have a sequence of positive integers M. You have a subset sum S of M, of elements in M. And then we have a binary sequence or a bit sequence, X. It's a sequence of zeros and ones, which we can easily convert into a subset sum. This simply tells you, looking at zeros or ones, which of these numbers to include and which not to include in your subset sum. Now, so this is not yet the cryptographic scheme. This is actually a little bit too easy. It would be too easy to break. But I want to explain just one sort of algorithm, if you like, that simplifies the just deciphering this simple part of it. So let me just explain a computational complexity matter connected with this kind of problem. So suppose we have a sequence M consisting of n positive integers. This is a sequence of n positive integers. So there is a one-to-one correspondence between n-term bit sequences, x1, x2, up to x of n, and subset sums. Bit sequence means all of the xi's are 0 or 1. And to every bit sequence, x1 up to xn, you take the sum, I goes from 1 up to n, xi, mi. So either if xi is 0, you're not counting mi in your sum. If xi is 1, you are counting it. You get s. And how many bit sequences are there? For each of these coordinates, their n coordinates, you have two choices, a 0 or 1. So there are 2 to the n bit sequences of length n. So given S, to find the bit sequence X, you have to do 2 to the n calculations. For every bit sequence, you compute the number S. You're trying to find a particular number S. You compute this sum until you hit S. It requires up to 2 to the n calculations. And if n is big, 2 to the n is very big. So there's actually a trick, a sneaky trick, called a collision algorithm, which reduces the number of subset sums you have to calculate. And it's such a pretty idea, I'm going to explain it. And it's the following. So again, recall we have M is a sequence of n integers, and X is a bit sequence of length n, and S is summation xi m sub I goes from 1 up to n. This is the bit sequence of zeros and ones that tells you what to calculate. So I'm going to write my number S. This is summation I goes from 1 up to n, xi mi. I'm going to break it up into two pieces. I have all the terms xi, mi, where I only goes up to n over 2, and then all the terms where I is bigger than n over 2 up to n. So my S is this plus this. Always. Could be this is 0 or this is 0, that's okay. But S is this sum plus this sum. Let me write it slightly differently. This is a sum of m sub I, where the i's are between 1 and n over 2, and the epsilon I is plus 1. And here I have a sum of the mi's, where the I is bigger than n over 2 and less than or equal to n, and the epsilon I is equal to 1. Or another way of saying this is a sum of m sub I for I in a set capital I, where capital I is contained in the integers from 1 up to n over 2. And this is a sum of, let me just call them m sub j's, where j is in a set capital J, where j is contained in the numbers, let's say n over 2, of n over 2, up to n. And this number I'll call a sub I, and this number I'll call a sub j. So ai is the sum of numbers in the first half of the terms of m, and aj is the sum of numbers in the second half. And it's pretty clear, I think, that if s equals ai plus aj, then then aj is, no, that's okay. That's certainly fine. So S minus aj equals ai. So S minus this equals this. And I'm going to call this number E sub j. So now you have to stare at this paper for a few minutes and observe the following. AI is a subset sum from the first half of the numbers from 1 up to n, just numbers from 1 over n, from 1 to n over 2. So let me write this over here. So there are not 2 to the n, but 2 to the n over 2 numbers ai. Similarly, the number aj comes from the second half of these n numbers, that is from a set of n over 2 numbers. So there are 2 to the n over 2 numbers a sub j, and s minus that, same number of numbers. And there are 2 to the n over 2 numbers bj, which is s minus aj. So to calculate all possible numbers ai, you do 2 to the n over 2 calculations. To calculate all possible numbers bj, you do another 2 to the n over 2 calculations. And then you just have to compare the AIs and the BJs. There has to be a collision. One of these must equal one of these if S is a subset sum. And how many calculations have we done? We've done 2 times 2 to the n over 2, plus what is, for a computer, very quick to compare 2 lists and see if they have an element in common. That's a searching and sorting procedure. So 2 to the n over 2, this is like, well, 2 power n over 2, that's a lot smaller than 2 to the n. Much, much smaller. This is like the square root of 2 to the n compared to 2 to the n. And this collision algorithm allows one to compute a subset sum much, much, much faster than just looking at all possible subset sums until you find one. Here, basically, you look at just a small fraction of the subset sums, you'll find your collision, and then you're done. In any case, this is an important technique in cryptography, but I still have not yet described our crypto system. One of the ambiguities that came up, we already saw, is that a certain number might have more than one subset sum. But there are certain sequences which have the property that a number is a subset sum in at most one way. And that happens for sequences which are called super increasing. So it's a sequence which is increasing very fast. So you have a sequence of integers, R1, R2, R3, and so forth, R sub I minus 1, Ri plus 1, up to R sub n. And the condition that makes it super increasing is that each number, Ri plus 1, is at least twice as big as the preceding number. So for example, if I take 2, the next number has to be at least 4. Could be 4. The next number has to be at least 8. Well, it could be 11. The next number has to be at least 22. I'll make it 23. The next number has to be at least 46. I can make it 50. So this is a super increasing sequence. Each number is at least 2 times as big as the one that precedes it. And a super increasing sequence has the property that if S is a subset sum of elements of integers in the super increasing sequence R, then S has a unique one and only one representation in composition as a subset sum. And in fact, there's a simple algorithm to find that representation. Let's see. We had a few terms for this. So this is a super increasing subset sum. Suppose I take S equals 151, and I tell you it is a subset sum from this sequence. So how do I find the terms that add up to 151? All I have to do is at every step is pick the largest number I can that could be an element in the subset sum. So 271 is too big, but I could take my first number to be 113. So this is 113 plus, let's see, what is left? 38, I think, plus 38. 38, if I want to write 38 as a sum of elements from here, the largest number I can pick is 23. So this is 113 plus 23, and then I have 15 left over. 15 The largest number I can pick is 11. And what's left is 4, and that's in there also. So this 151 is a sum of 113, 23. Oops, it said 15, but this is actually an 11. So this should be 113 plus 23 is 136, which left 15. 15 was 11 plus 4. So this is 113 plus 23 plus 11 plus 4. For a super increasing sequence, the algorithm, the computer program you write to represent an integer as the sum of elements from the sequence, is at every step you pick the largest number you can. Sometimes called a greedy algorithm. Just pick the biggest thing you can get. And this is described in slightly different language in this proposition 7.5 in this section. There it's written as a computer program. Okay. So how do we construct from this a crypto system? The idea is if I simply, so here is what I'll say is the bad idea. Publish a super increasing sequence R, R1, R2, and so forth. And you define encryption as follows. If your plain text, the message you want to encrypt, is a binary sequence, x1, x2, up to x of n, then the person sending you the message sends you the subset sum s equals summation xi ri. It goes from 1 up to n. And when you get s, you can easily find the subset sum that gives you s, so you found the binary sequence x. The problem with this is, of course, that it's easy for this to be decrypted, not just by you, but by anyone who knows what the sequence is, and you've made this sequence public. So as a method of transmitting information, this is excellent. But as a method of transmitting information securely, this is terrible. So the way you modify this is as follows. So again, we have our super increasing sequence, R1, R2, up to R sub n. And we choose an integer b, which is bigger than twice the largest number, 2r sub n. And we choose another positive integer a with the GCD of a and b equal to 1. So you choose a large number b and you choose a number a relatively prime to b. And from this, you construct a new sequence. So let the number m sub I be equal to ri times b, ri times a ari mod b for all I from 1 up to n. That is, you take each of these numbers, multiply it by a, and take the least non-negative element of the congruence class, mod b. So now you have a sequence M, which consists of n different numbers. If a is prime to m, ARI, the ARR is a different mod B. A is prime to B, which is no longer super increasing. It's just a sequence. And you publish M. So everyone in the world knows your sequence M. So Alice is the one who's setting up this crypto system. She chooses a super increasing sequence R. She chooses a number B bigger than 2Rn, the largest one. And she chooses a number A relatively prime to B. She constructs a new sequence of integers, Mi, where Mi is congruent to A times Ri mod B for all I. She publishes this sequence M. And what is the encryption method? So Bob has a bit sequence X, which is X1 up to Xn, that he wants to transmit to Alice. Bob. And what Bob does is, or anyone who wants to send a message to Alice, he computes the number S, which is summation X sub I, M sub I. I goes from 1 up to N. So M is not super increasing. M is complicated, just some strange sequence of numbers. And Bob takes the subset sum corresponding to his bit sequence, and he sends this to Alice. And of course, the eavesdropper, Eve, can intercept this number. She has this number. She would like to find the X's. But there's no structure to the sequence M that's obvious. And the only way Eve can find this number S would be to actually find the subset sum that gives you S. And that's a hard problem. So just the way the discrete logarithm is hard and factoring an integer is hard, if you know a number is a subset sum of integers in a set, to find those integers that make up the number that you add together to make up the number, that's hard. So Eve doesn't know what to do. But what does Alice do? Alice receives this message S. So S is summation Xi Mi. I goes from 1 to N. Because, so again, and we always use this bit of number theory, because A and B are relatively prime, A has an inverse mod B. There is an integer, I'll write it as A to the minus 1, such that A inverse A is congruent to 1 mod B. So what Alice does is Alice calculates A inverse S mod B. And I claim this allows her to decipher the message, to find the message X that Bob wanted to send to her. Why is that? Well, A inverse S is A inverse is an integer, summation Xi Mi. I goes from 1 up to N. You want to take just congruence classes mod B. What is M? M is AR sub I. So this is summation A inverse, or anyway, summation I goes from 1 up to N. A inverse X sub I, Let me do this on a clean sheet of paper. So S is summation xi mi. That's the number which is sent to Alice. Alice computes A inverse S. What is this congruent to? Mod B. This is A inverse summation I goes from 1 up to n, xi, m sub I. This is congruent to summation I goes from 1 up to n, xi, A inverse m sub I. We're just doing everything mod B. This is summation I goes from 1 to n, x sub I, A inverse, and m sub I was ARI mod B. And A inverse A is 1. So this is summation x of I goes from 1 to n, A xi Ri mod B. And just to make a quick remark, summation xi Ri, I goes from 1 up to m. The x's are 0 or 1, the ri's are integers. This is certainly non-negative. The biggest this can be, goes r up to n, the biggest this can be is if all the x's is 1. This is summation I equals 1 to n, r sub I. That's less than, actually strictly less, than 2r sub n. Because this is super increasing. Rn is bigger than the sum of all the previous numbers, which is less than or equal to b. We chose b to be bigger than 2Rn. So in fact, A inverse S is equal to summation xi Ri. I goes from 1 up to n. And what we have here is a subset sum of the super increasing sequence R1, R2, up to R sub n. And we saw that there is a very fast, really trivial algorithm to take a subset sum of a super increasing sequence and find the summands, the numbers that add up to it. So Alice does that, and she finds the x's, the x1 up to xn. So she's recovered the binary sequence, the secret message that Bob wanted to send to her. And that is the subset sum crypto system. That's exactly it. So this doesn't use factoring or discrete logs, it uses other kinds of mathematics. And it is a very, very beautifully constructed crypto system. So this is the third crypto system in your cryptography toolkit. That's what I needed to tell you about.